Okay, we're continuing our pairwise comparisons as a follow-up to analysis of variance. And I entitled this one effect size statistics because it's an important variation of the pairwise comparisons. So we're asking a slightly different question. We are actually not interested in whether our treatments are different, but by how much. So we already covered the type 1 error, inflation, and experiment-wise alpha level issues. Those apply to effect size statistics just as much as they do to the pairwise comparisons. And also the signal to noise ratio boost applies, so we should, just as with the pairwise comparisons, we should do effect size statistics with the output from analysis of variance. What's different is the reporting. So the reporting will be confidence intervals or one-sided p-values typically, and I'll show you how to do this. So one of the problems is that people recognize that this blind statistical null hypothesis testing has no value, but they just don't know what else to do. And so in many fields, effect size statistics are simply not taught because nobody knows it. So I'll mark this one with a star. This is here a really valuable addition for any kind of applied statistical science field. That is the way to go. So forget the pairwise comparisons, except in the very few circumstances where you actually have a null hypothesis that you don't already know that it's false. So this can happen, but it's very rare in the applied sciences. Now let's continue with effect size statistics. So those are a little bit more explicit, and you have an expectation, so you're not just asking, is there any difference between whatever comes out of the ANOVA? You have some idea, you have some reason why you want to test things, and you have an expectation or an objective that you want to accomplish. So 90% of the cases, forget about pairwise comparisons, just as I showed you. This is the important part. So it's a follow-up just the same way. It's in principle nothing different. I'm just going to rerun this here to have our linear model in memory. And so now what I do is I have to specify the questions that I'm interested in. So if you remember my story that I used for illustration here, our variety A, that's the new discovery, right? So this was my 728 kilogram per hectare, and that was so much better than the typical 500 control variety. So what I did is I compared A to two control varieties, so B and C are the typical stuff that the company sells, and I put 2 just to be sure, but what I'm really interested in is A. So I want to test whether A is not only different from B, but I got a mission from my boss, right? If you remember that story as well. So I wanted at least 30% gain before that gets marketed and rolled out in a big way. And so I have to specify these comparisons here as alternative hypotheses. So my first alternative hypothesis is that the difference between A and B is larger than a particular value. And the way that I specify A and B is with this string here. So this would be A, that's specified as a 1, and B is specified as a -1, so I subtract B, that's my difference. And the 0 here means that C has no role in this particular comparison. And the same here, A minus C, I specify as A minus C here, and in this case that B has no role. So you have to formulate your alternative hypotheses in this little table. Let's just execute this, Control R. And let's take a look at this. So you could also prepare this little table in Excel and import it, but it's easy enough to just program it. And it can have as many rows as you have questions that you want to answer from your significant ANOVA effect. So, and I have 2 rows here. Now I also have to specify the 2 differences. And a 30% improvement over B is 152 kilogram per hectare, and for C it's a little bit more because there was a bigger variety, so 154. So let's also create this string here, and it's just those 2 numbers. So now I can test this just as I did the comparison before with a slightly different command. So this glht is part of the multicom package, and it takes the output file with the pooled variance that we want, and then I do a multi-comparison of variety using the alternative hypothesis table here that we specified, and the differences here that we specified. And our alternative hypothesis is that it's greater, right? So A minus B should be a larger number than 152 or 154. So let's run this and take a look at it. And sure enough, A minus B larger than 152. I can claim that I get that 30% gain with 99.5% probability, and in this case with 99.1% probability for variety C. So those are the cool statements that you want to make. We can also do it the other way around. So you can look at different confidence intervals. So they'll be one-sided because I specified this here as greater. So if we look at a 95% confidence interval, I can turn this statement around. I preset the probability and now I get the value. So I can say that with 95% probability, I get 179 kilogram per hectare improvement at least, and 173 for C. Now if I lower my confidence a little bit, I get 200, 212 with a 50% chance, and if I'm lucky, 1 out of 4 times, I would even get 225 kilograms per hectare. So that I can communicate as well. Or I can do the same for the original version here and just preset different values. So I calculated a 35% gain, 40% gain, and 45% gain here. So it's the same as this, just with different values. So I can run those all and I can get my probabilities for those. So in this case, I get a 35% gain with 96% probability, a 40% gain with 70% probability. So now it starts dropping off, and I can guarantee a 45% gain with just 16% probability. So my confidence in those increasingly bigger promises that I make drop eventually to 0, right? But if you can convey these uncertainties and those probabilities, that's both the minimum what you can promise and the maximum that it can likely be. So both of those pieces of information are important for decision makers in most cases. So we can again look at how this would be reported. So either you preset your p-values here at particular confidence levels and you just report the gains that you can accomplish, or you can preset the gains here. So in this case, I don't do it in kilogram per hectare, but just in 35, 40, and 45% gain. And then you report the probability. So just what we calculated there, 96, 69, and 16% probability that I get 45% gains, and then the same for C. So these are very compact and small and informative tables. Those are the ones that make an impact. And the funny thing is that really nobody knows how to do this. That's really interesting, isn't it, right? So what you learn in this class, I would say 99% of university graduates don't actually know how to do this, right? Everybody only knows how to do this. And this is kind of useless. I mean, if you are a manager, you can still look at the confidence intervals here and you can say, well, okay, probably that's a good idea. Let's go with this. If that's a prescription, that's not too expensive to implement. But it's nothing in terms of precision and information density as these types of tables. So you should almost always consider to do the effect size statistics. In R, it's just 1 or 2 lines of code really, and you rerun them with different values to get both the minimum that you can expect and the maximum potential that can be inferred from your experiment. So that is really the valuable stuff. So with that, I let you do Lab 7. And Lab 7 contains everything that we've done in the past 4 videos. So you can take your time and work through all this.